Every second, across every inch of space, the universe is screaming secrets we can barely comprehend. We gaze into the night, seeing only ancient echoes ghostlight from a past that is profoundly, terrifyingly alien. We've built monuments of glass and silicon, pushing our sight to the very edge of existence, yet what we see is a mere whisper, a shimmering, transient illusion. 95% of reality remains an invisible, unfathomable force, ripping space apart, bending light and shaping the very fabric of everything we know. Galaxies are vanishing from our view, stars are being born in hidden dust, and the earliest moments of creation are sealed behind an impenetrable wall of fire. The cosmos isn't just bigger than we imagined. It's stranger, more elusive and fundamentally unknowable, in ways that challenge the very core of our understanding. If this dive into the unknown has you intrigued, go ahead and subscribe, we're only at the beginning. Brace yourself. The reality ahead is far stranger than it appears. The observable universe, a cosmic bubble of light and time, stretches an incomprehensible 93 billion light-years across. Yet this vast expanse, every star, every galaxy, every particle we have ever detected, touched or even dreamed of, constitutes a mere 5% of all that truly exists. The remaining 95% is hidden in plain sight, a silent, dominant architect of reality. Light, the universe's ultimate messenger, races at an astonishing 186,000 miles per second. Intuitively, we might assume that if the universe is 13.8 billion years old, our cosmic reach would be limited to 13.8 billion light-years in any direction. But the cosmos, in its infinite complexity, defies such simple arithmetic. Astronomers have confirmed a truth that makes even the most seasoned physicists pause. The observable universe extends an astonishing 46 billion light-years from Earth in every direction, forming that colossal 93 billion light-year sphere. How can light from a galaxy 40 billion light-years away possibly reach us when it only had 13.8 billion years to travel? The answer lies in the dynamic, evolving nature of space itself. Imagine a cosmic treadmill constantly expanding beneath the very light photons trying to reach us. While the ancient light began its journey, the universe stretched and grew, carrying the emitting galaxy further away, even as its light progressed. We are not seeing these distant galaxies where they are now, but where they were billions of years ago. Frozen snapshots of their ancient selves, their current locations lying far beyond where they first appeared. This relentless cosmic expansion creates a paradoxical truth. The edge of what we can observe is constantly growing, yet we will never truly catch up. Each year, new ancient light reaches us from regions that were previously beyond our cosmic horizon, expanding our visible sphere by 1 light-year in radius. It's like standing in an infinite, slowly dissipating fog bank. More landscape perpetually appears, but the true horizon continues to recede, ensuring that the vast unseen territory never truly shrinks. The sheer scale quickly overwhelms the human mind. Within this theoretically observable volume, astronomers estimate there are between 200 billion and 2 trillion galaxies. Each of these galaxies in turn harbours billions, even trillions of stars. To grasp this, consider an analogy. If every single star in the observable universe were represented by a solitary grain of sand, you would require more sand than exists on all the beaches of Earth. Then multiply that colossal sum by several hundred times over. We're talking about a minimum of 10,000 billion stars, and quite possibly many more, all contained within our cosmic bubble. Yet this unfathomable number represents only what light has had time to reach us. Beyond this observable sphere, more universe undoubtedly exists. How much more that remains one of the universe's most profound unanswered questions. Space might extend infinitely in all directions, a boundless cosmic tapestry, or it might subtly curve back on itself, forming a finite but endlessly looping expanse. Scientists genuinely do not know. What they do know only deepens the enigma. Recent painstaking measurements suggest the actual universe is at least 250 times larger than the portion we can observe. Some theoretical calculations push this figure to infinity itself. But even infinity holds limits when we're confined within our cosmic bubble. What unfolds beyond our horizon might as well exist in an entirely different reality, permanently veiled from our perception. For decades, astronomers diligently catalogued everything they could detect: stars, galaxies, gas clouds, planets, black holes, every whisper of radiation. They painstakingly added up all this visible matter and energy. The total consistently came to roughly 5% of what the universe should contain, according to the undeniable dictates of gravity. 5%. Everything humanity has ever seen, touched, or directly detected makes up a mere 1/20th of reality. The magnitude of this realization struck the scientific community like a seismic shockwave in the late 1990s. Observations of distant supernovae exploding stars that serve as perfect cosmic measuring sticks unveiled a chilling truth. The universe wasn't merely expanding, it was accelerating. Something invisible, pervasive, and utterly unknown was actively pushing space apart. Simultaneously, astronomers measuring the rotation speeds of galaxies found them spinning too rapidly. An unseen gravitational force was holding them together, preventing them from flinging their stars into the void. This wasn't a flaw in our instruments or a mathematical error. Multiple independent observations from the largest galaxy clusters to the faint ripples in the cosmic microwave background radiation consistently confirmed it. Galaxies behave as if they contain 10 times more mass than we can detect. Clusters of galaxies move as if bound by gravitational forces far stronger than visible matter could possibly produce. The cosmic microwave background itself, a fossil echo of the Big Bang, displays patterns of ripples that only make sense if invisible matter dominated the early universe. Scientists facing the humbling reality of their ignorance coined names for what they could not see: dark matter and dark energy. Do not let these innocuous labels mislead you. These are not speculative theories awaiting confirmation. They're confirmed unknowns, phenomena that definitively exist but whose fundamental nature remains a complete perplexing mystery. We know with absolute certainty that something is there. We have measured its profound effects thousands of times. We just have zero idea what it actually is. Dark matter accounts for roughly 27% of the universe's total mass-energy budget. It possesses mass exerts gravity and subtly bends light through gravitational lensing. Facts confirmed by countless observations. Galaxies are not solitary islands in the cosmos. They swim through vast unseen clouds of dark matter. Some dark matter halos are so immense they contain 100 times more mass than all the stars they envelop. We have painstakingly mapped its distribution across the cosmos using its gravitational fingerprints, yet we have never touched it, never directly detected a single particle of it. It doesn't absorb light, doesn't emit light, and interacts with normal matter only through the weakest whisper of gravity. Imagine trying to study something that only makes its presence known by subtly pulling on everything around it. Dark energy. The universe's most dominant component makes the situation even more unsettling. It accounts for a staggering 68% of everything. Its existence is confirmed through multiple lines of evidence, yet it appears to be an intrinsic property of space itself. Empty space, it turns out, is not truly empty. It possesses energy, and as space expands, more dark energy spontaneously comes into existence, fueling the acceleration. It is currently winning a cosmic war against gravity, inexorably driving galaxies apart across the larger scales. Here's what truly keeps physicists awake at night. We inhabit a universe where we can directly observe less than 5% of what exists. The other 95% actively shapes everything. How galaxies form, how the universe expands, how clusters hold together, yet remains fundamentally invisible and mysterious to us. The cosmos we believe we know is merely the visible foam on an ocean we can barely fathom. Galaxies spin like colossal cosmic pinwheels, yet by all known physics they shouldn't hold together. Stars on their outer edges move so fast that the visible matter alone cannot possibly keep them bound. They should fly off into the vacuum of space like water droplets, flung from a rapidly spinning wheel. Yet they don't. Something invisible, immense and powerful grips them. Astronomers first grappled with this problem in the 1930s, when Fritz Zwicky, studying the Coma cluster, noticed its galaxies moved at such extreme speeds that the cluster should have torn itself apart billions of years prior. Zwicky calculated the cluster needed 400 times more mass than he could visually detect to generate sufficient gravity. He called it dunkle materie, dark matter. Most scientists dismissed his findings for over 4 decades. Then, in the 1970s, Vera Rubin meticulously measured the rotation curves of spiral galaxies. Every single galaxy she observed displayed the same impossible pattern. Stars far from the galactic centre moved almost as fast as those near the core. The rotation curve remained stubbornly flat instead of dropping off as predicted by orbital mechanics based on visible matter. Only one explanation coherently fit these observations. Invisible matter formed massive diffuse halos around galaxies extending far beyond their visible edges. These halos contained substantially more mass than all the star's gas and dust combined. The ratio was shocking, roughly 6 times more dark matter than normal matter in a typical galaxy. Computer simulations further cemented this understanding. When dark matter is incorporated into models of galaxy formation, the resulting structures precisely match what our telescopes observe. Remove it, and galaxies simply don't form. The early universe would have remained a nearly uniform soup of gas. Dark matter's gravity provided the initial scaffolding, the unseen framework into which normal matter subsequently fell, creating the gravitational wells that fostered galaxy birth. The evidence became overwhelmingly robust. Gravitational lensing, where the gravity of massive clusters bends light from distant galaxies, provided direct maps of dark matter's distribution. By measuring the distortion of background galaxies, astronomers traced vast filaments, nodes and voids, a cosmic web woven from invisible material. The Bullet cluster in 2006 provided the smoking gun. This was a direct collision of 2 galaxy clusters. Normal matter glowing hot in X-rays was slowed by friction during the impact. But the dark matter passed right through, creating gravitational lensing effects, far from the visible gas. This proved dark matter exists as an actual substance, not merely a mathematical fudge factor. Normal matter collided and lagged. Dark matter was collisionless, just as theory predicted. But what is it made of that remains the confirmed unknown mystery? Scientists have proposed dozens of candidates: WIMPs, weakly interacting, massive particles, axions, sterile neutrinos, even primordial black holes. Massive detectors buried deep underground to shield them from cosmic rays tirelessly search for dark matter particles subtly bumping into normal atoms. So far nothing. Every experiment returns empty-handed, yet the gravitational evidence relentlessly mounts. Dark matter definitively exists. It outweighs normal matter by a factor of 6 to 1 across the universe. It formed the structure we observe. It holds galaxies together right now. We just cannot figure out what it actually is, and that unnerves some physicists, suggesting our fundamental understanding of matter itself might be catastrophically incomplete. In 1998, 2 independent teams of astronomers made a discovery that shouldn't have been possible. They were studying Type Ia supernovae, exploding stars that consistently shine with nearly identical peak brightness, making them perfect cosmic standard candles, or distance markers. By measuring their apparent brightness, you can calculate their distance. Both teams fully expected to find the universe's expansion gradually slowing down. Gravity, the universe's pervasive attractive force, should inexorably break cosmic expansion, right? Every mass in the universe pulls on every other mass. The data told a different startling story. Distant supernovae appeared dimmer than predicted, meaning they were significantly farther away than they should have been. The universe hadn't been slowing down, it had been speeding up. Expansion was accelerating. Physicists meticulously checked the math countless times. The observations held up. Something was pushing space apart with ever-increasing strength. The discovery earned a Nobel Prize and simultaneously unleashed an existential crisis in cosmology. Scientists called it dark energy, a name that reveals precisely nothing about its true nature. Unlike dark matter, which clumps around galaxies, dark energy appears to uniformly permeate all of space. It exerts a negative pressure, a repulsive force that actively counteracts gravity on cosmic scales. Here is the confirmed measurement: dark energy comprises a staggering 68% of all energy in the universe. It is the dominant component of reality. Every cubic meter of empty space contains this mysterious energy. And as space expands, more dark energy spontaneously comes into existence. The universe, it seems, creates new energy from nothing as it grows. This defies human intuition about the conservation of energy, yet the mathematics checks out under Einstein's general relativity. Space itself can possess energy as an inherent property. Einstein, in fact, predicted something akin to this with his cosmological constant, a value he later famously called his biggest blunder. It turns out he was right the first time. The effects are measurable and frankly terrifying. Right now, dark energy is winning its war against gravity. Clusters of galaxies that are gravitationally bound will remain together, but everything beyond our local supercluster is accelerating away from us. Eventually, trillions of years from now, galaxies outside our gravitational neighborhood will recede faster than light can travel. Their light will never reach us. They will fade from view one by one until observers in the unimaginably distant future will gaze upon a mostly empty universe. The cosmic microwave background, the ancient afterglow of the Big Bang, will be redshifted into invisibility. Evidence of the Big Bang itself will vanish. But here's what truly disturbs physicists: we have absolutely no idea what dark energy is. The leading theory suggests it's a property of space itself: vacuum energy. Empty space, even when devoid of all matter and radiation, naturally contains energy according to quantum mechanics. But when physicists calculate how much vacuum energy, quantum mechanics predicts they arrive at a number 120 orders of magnitude too large. That is not a typo. The prediction is off by 1 followed by 120 zeros. It is unequivocally the worst prediction in the history of physics. Something is catastrophically wrong with our fundamental understanding of reality. Yet the measurements keep coming in. Dark energy exists. It is accelerating cosmic expansion. And we are completely baffled as to why. In 1995, Robert Williams, then director of the Space Telescope Science Institute, wielded a unique power. He controlled 10% of the Hubble Space Telescope's invaluable observation time. He could point humanity's most advanced eye at anything in the universe. He chose to aim it at nothing. Williams selected a tiny, unremarkable patch of sky in the constellation Ursa Major. To ground-based telescopes, this region appeared utterly empty. Just blackness. No bright stars, no obvious galaxies, nothing of apparent interest. His colleagues openly questioned if he was squandering precious telescope time. Williams, however, believed otherwise. He suspected that a sufficiently long exposure might reveal faint distant galaxies that no one had ever seen before. From December the 18th to 28th, Hubble stared relentlessly at this seemingly empty patch for 10 consecutive days, combining 342 separate exposures into one monumental image. The result irrevocably changed astronomy. The image revealed roughly 3,000 galaxies. Not stars, but entire galaxies, each harboring billions of stars. They filled every corner of the frame, from bright majestic spirals in the foreground to faint reddish smudges representing galaxies over 12 billion light-years away. Some were so distant their light had travelled for most of the universe's entire history. The Hubble Deep Field covered a patch of sky equivalent to a tennis ball seen from 100 yards away, or a single grain of sand held at arm's length, an infinitesimally small pinprick of the heavens. In this minuscule slice of apparent nothingness, 3,000 galaxies appeared. Do the math, the entire sky contains roughly 12 million such areas. If every patch contained 3,000 galaxies, the universe held tens of billions of galaxies minimum. Previous estimates had been wildly conservative, but the true revelation came from the galaxies themselves. They displayed incredible variety: spirals, ellipticals, irregular blobs, galaxies colliding, galaxies actively forming. Many looked nothing like modern galaxies. They appeared more chaotic, more active, decidedly stranger. Astronomers realized they were witnessing galaxy evolution across cosmic time. The farthest galaxies in the image existed when the universe was less than 1 billion years old. Their light had been travelling towards Earth for over 12 billion years. In that immense span of time, these distant galaxies had evolved, merged, and likely transformed into massive elliptical galaxies by now. We were seeing their baby pictures. The scientific community produced over 900 papers based on this single image, making it one of the most analysed photographs in astronomy. But Williams wasn't finished. In 2004, Hubble went even deeper with the ultra-deep field 11 days of exposure revealing nearly 10,000 galaxies. Then in 2012, the extreme deep field pushed even farther, capturing galaxies 13.2 billion light-years away. Each progressively deeper image revealed the same astonishing pattern. Point anywhere in the apparently empty sky stare long enough, and thousands of galaxies appear. The universe is far more crowded than we ever imagined. Yet here's the haunting part: these deep fields, even combined, cover less than 1/1,000,000th of the entire sky. We've seen incredible detail in these tiny patches, but they are mere needles in an infinite cosmic haystack. What else is hiding in the darkness waiting for us to look? Astronomers frequently announce they've surveyed the universe. Press releases celebrating massive sky surveys encompassing millions of galaxies. The numbers sound impressive until you examine the actual fraction of the sky observed in detail. The Sloan Digital Sky Survey, one of the most comprehensive projects ever undertaken, mapped about 1/3 of the entire sky. That sounds substantial, but here's the catch. Even this massive survey only detected galaxies down to a certain brightness limit. Faint galaxies, and there are billions of them, remain invisible. The Dark Energy Survey spent 6 years photographing the southern sky, covering 5,000 square degrees total, cataloguing hundreds of millions of objects. Impressive work, but that still represents roughly 1/8 of the sky. 7/8 remained untouched by their detailed observations. The Euclid Space Telescope, launched in 2023, aims to survey 15,000 square degrees. When complete, this will cover about 1/3 of the sky, making it the most ambitious mapping project ever attempted. Yet 2/3 of the heavens will still remain outside its field of view. Now consider the critical trade-off: depth versus coverage. The deeper you look into the universe, the smaller the area you can observe in a reasonable amount of time. The James Webb Space Telescope can see incredibly distant galaxies, but its field of view is minuscule. Imagine trying to map an entire continent by looking through a straw. You'll see amazing detail in small patches, but massive areas go unexplored. The Cosmos Web project recently compiled nearly 800,000 galaxies, reaching back 13.5 billion years. The research team hailed it as the most comprehensive cosmic map ever created. The survey area less than 1 square degree of sky. The full sky contains roughly 41,000 square degrees. Do that division, the most comprehensive deep survey covers about 0.2% of the sky. We've achieved incredible depth in an area smaller than the apparent size of the full moon. Such trade-offs are unavoidable with current technology. Telescope time is severely limited. Every hour spent staring at one patch means other regions go unobserved. Survey teams must choose map-wide areas with less detail, or probe deep into tiny regions. Most surveys prioritize wide coverage catalogue in millions of nearby galaxies across large portions of the sky. This reveals the large-scale structure, how galaxies cluster into filaments and walls. But these surveys inevitably miss the faint, distant galaxies that deep exposures would reveal. A handful of projects, however, choose depth, producing exquisite images of small fields. These reveal the distant universe in unprecedented detail, but their narrow view creates sampling problems. Perhaps they happen to point at an unusually crowded region or an unusually empty one. Small sample sizes inherently introduce uncertainty. What this means practically is that comprehensive maps of the nearby universe exist. Astronomers have catalogued galaxies within a few billion light-years fairly well. Beyond that distance, coverage becomes increasingly spotty. We have spectacular, highly detailed images of tiny areas interspersed with vast, unexplored regions. The total fraction of sky that has been deeply surveyed, meaning long exposures revealing faint distant galaxies, amounts to far less than 1%, probably closer to 0.1%. 99.9% of the deep universe remains unsampled, unobserved territory. Literally anything could be hiding there, and we would have no idea. Our own galaxy, the beautiful Milky Way, is sabotaging our view of the universe. It stretches across the night sky as a luminous band of stars and gas, a breathtaking spectacle. But for astronomers attempting to study distant galaxies, it creates a massive blind spot, a cosmic zone of avoidance. This obscured region covers roughly 20% of the sky, the areas where the Milky Way's disk lies between us and the deeper universe beyond. The primary culprit is dust. Our galaxy contains vast opaque clouds of cosmic dust, tiny particles of carbon, silicon and other elements. These clouds relentlessly scatter and absorb visible light. When astronomers attempt to observe distant galaxies through the zone of avoidance, the dust blocks their view like trying to see through a dense fog. Some of the most interesting cosmic structures, perhaps even paradigm-shifting ones, might be hiding there. The Great Attractor, a massive gravitational anomaly pulling our entire galaxy cluster, lies partially behind this very zone of avoidance. Astronomers know something enormous exists there because they can measure its powerful gravitational effects on surrounding galaxies, but direct observation is exceptionally difficult. In 2021, astronomers discovered the South Pole Wall, a colossal structure containing hundreds of thousands of galaxies stretching across 1.4 billion light-years. It had remained hidden partially because it lies deep within the zone of avoidance. Researchers only found it by employing radio telescopes, which can penetrate dust far better than optical instruments. How many other structures, how many other cosmic secrets remain concealed? The zone of avoidance could conceal entire superclusters, major galaxy filaments connecting visible structures in ways we have not yet mapped. We are essentially trying to understand cosmic geography, while 20% of our map is permanently covered by a giant swirling smudge. Infrared and radio observations offer a way to pierce this veil. These longer wavelengths penetrate dust far more effectively than visible light. Surveys at these frequencies have successfully revealed previously hidden galaxies within the zone of avoidance. Thousands of galaxies have been discovered this way in recent decades, but infrared observations come with their own limitations. Telescopes sensitive to these wavelengths are harder to build and operate. Earth's atmosphere blocks many infrared frequencies, necessitating expensive space-based observatories. Even the best infrared surveys don't match the depth and resolution of optical surveys in clearer parts of the sky. The 2-micron all-sky survey, TWAS, and the WISE satellite have catalogued millions of infrared sources through dusty regions. These projects revealed that the Milky Way's zone of avoidance isn't completely impenetrable. It's more like translucent, a murky window rather than an opaque wall. We can see through it with enough effort and the right instruments, but the view remains indistinct compared to clear sky areas. Consider what this means for our understanding of large-scale cosmic structure. Imagine trying to map ocean currents, while 20% of the ocean is perpetually covered by thick fog. You can infer some things from the patterns you see in the clear areas. You can use indirect measurements to detect major flows beneath the fog, but you are definitely missing critical information. Galaxy surveys systematically avoid the zone of avoidance. Most large catalogues have glaring gaps where the Milky Way obscures the view. These gaps inevitably create uncertainties in measurements of cosmic structure. Are the filaments and voids we observe truly representative of the whole universe? Or have we missed major features hiding behind our own galaxy? Some researchers believe the zone of avoidance conceals structures that would fundamentally alter our understanding of the local universe's architecture. Others suspect nothing particularly unusual lurks there, just more of the same cosmic web we see elsewhere. Both groups agree on one thing we won't know for certain until we develop better ways to pierce the veil. Our own galaxy paradoxically ensures vast regions of the universe remain mysterious, possibly hiding surprises that would transform cosmology. In February 2025, astronomers announced they had found something that by conventional understanding shouldn't fit together. A superstructure so massive it challenged theoretical limits on how large cosmic structures could possibly grow. They named it Quipu after the ancient Incan recording system of knotted strings. A fitting name for this cosmic giant resembles a vast filament with smaller strands branching off galaxy clusters linked together like knots on a cosmic thread. Quipu stretches an astonishing 1.4 billion light-years from end to end. To put that into perspective, light travelling at its cosmic speed limit takes 1.4 billion years to cross it. This colossal structure contains 68 galaxy clusters, each cluster holding hundreds or thousands of galaxies. Its total mass is estimated at 200 quadrillion times the mass of our Sun. This sheer scale brazenly violates existing expectations. According to standard cosmological models, the universe simply shouldn't have had enough time since the Big Bang for structures this large to form through gravitational collapse. Gravity, while powerful, works slowly on cosmic scales. Structures grow as matter clumps together, but there are inherent limits. The theoretical maximum size calculated from the universe's age and expansion rate suggests structures should not exceed approximately 1.2 billion light-years. Quipu exceeds this by 200 million light-years. While that might not sound like much in cosmology, it is profoundly significant, akin to discovering a human who stands 10 feet tall when the theoretical maximum height is 8 feet. Quipu isn't alone. The same research team identified 4 other superstructures approaching similar boundary-pushing sizes: the Shapley supercluster, the Serpent's Corona Borealis superstructure, the Hercules supercluster, and the Sculptor Pegasus superstructure. Together, these 5 cosmic giants contain a staggering 45% of all galaxy clusters within their distance range, nearly half the matter in that entire region of space. These structures span the sky from the southern to the northern hemispheres. Quipu alone can be traced across multiple constellations from Pictor and Carina in the south, through Puppis, Lepus, Eridanus, Taurus Triangulum, all the way to Perseus in the north. It utterly dominates a massive swathe of the observable universe. The discovery emerged from analysing X-ray data from the Rosat satellite. Galaxy clusters contain superheated gas that glows brilliantly in X-rays. By mapping these X-ray bright clusters and calculating their distances using redshift measurements, researchers meticulously reconstructed the 3-dimensional structure of the local universe. When they plotted cluster positions, Quipu jumped out immediately. One researcher noted that the structure is readily noticeable by eye in a sky map of clusters without needing sophisticated detection algorithms. It's just sitting there obvious once you know where to look. But finding it raises unsettling questions. If structures this large exist in the relatively nearby universe, Quipu lies between 425 and 815 million light-years away. What lurks in the more distant cosmos? Deeper surveys haven't yet reached the sensitivity needed to detect similar structures at greater distances. They might be out there hidden by their extreme remoteness. Quipu also creates practical problems for cosmologists. These massive structures subtly warp the cosmic microwave background radiation passing through them. They create gravitational distortions that affect measurements of the universe's expansion rate. Scientists must meticulously account for these effects when calculating fundamental cosmological parameters. The structure, however, won't last forever. The universe's relentless expansion will eventually pull it apart. Computer models suggest Quipu will fragment into several collapsing units as dark energy inexorably drives space apart. In the far future, what we now perceive as one connected structure will become separate isolated clusters. For now, Quipu represents a physical entity demanding attention, a confirmed structure whose size pushes the boundaries of what physics says should exist, and it makes astronomers wonder what else might be hiding in the darkness even larger and stranger. Between the grand filaments and the clustered superstructures, something even stranger exists. Vast, desolate regions of space containing almost nothing. These cosmic voids stretch hundreds of millions of light years across with barely any galaxies inside them. The Bhuta's Void, one of the first discovered, was found in 1981 during surveys of galaxy distributions. This colossal void spans 330 million light-years in diameter. Inside it, based on the universe's average density, astronomers expected to find roughly 10,000 galaxies. They found a mere 60 galaxies in a volume that should contain 10,000. The void is 99.4% empty compared to what it should be. These are not just empty spaces where galaxies happen to be sparse. Voids possess distinct edges, well-defined walls of galaxies surrounding nearly empty interiors. It's as if the universe organized itself into a gigantic foam. Galaxies clustering on thin sheets and filaments surrounding enormous bubbles of mostly empty space. The largest known void, the giant void in the constellation Canes Venatici, measures roughly 1 billion light-years across. Imagine a sphere 1 billion light-years in diameter, containing just a handful of galaxies. Cross it at light speed, and the journey would take 1 billion years, during which you would pass almost nothing. Voids are not completely empty. They contain dark matter, just far less of it than average regions. Tenuous filaments of hydrogen gas thread through them, and occasional dwarf galaxies huddle in the darkness. But compared to the rest of the universe, voids are eerily vacant. Their existence reveals something fundamental about cosmic structure formation. In the early universe, tiny quantum fluctuations in density became magnificently amplified by expansion. Denser regions attracted more matter through gravity, becoming even denser. Less dense regions lost matter to their surroundings, becoming even emptier. Over billions of years, this process created the cosmic web, the largest structure pattern in the universe. Dense regions collapsed into galaxy clusters. These clusters connected along filaments. Between the filaments, voids expanded as their sparse matter drained inexorably towards denser regions. The process is still happening. Voids are growing. Their sparse matter continues migrating towards surrounding walls of galaxies. In the far future, voids will become even emptier, as the last straggling galaxies either collapse into their centers or escape to the walls. Some voids show substructures, smaller voids within larger voids, creating a fractal-like pattern. The local void, roughly 150 million light-years across, sits near our Milky Way. We are positioned close to its edge, looking into a relatively empty region of space. Galaxies inside voids look different from those in denser regions. They tend to be bluer, younger, and more actively forming stars. Their isolation protects them from the violent interactions and collisions that would trigger rapid evolution in crowded environments. Void galaxies are cosmic hermits, evolving in slow motion compared to their bustling cousins in clusters. The Eridanus supervoid presents a different mystery. This massive void appears to create a cold spot in the cosmic microwave background radiation, a region where the ancient light from the Big Bang appears slightly cooler than surrounding areas. The void's presence might explain this anomaly, though the physics remains controversial. Mapping voids helps cosmologists test theories of structure formation. Computer simulations that include dark matter naturally produce cosmic webs with voids similar to those observed. Remove dark matter from the simulations and the void structure doesn't form correctly. This provides indirect evidence that dark matter exists and actively drives structure formation. But voids also raise unsettling questions. Why did the universe organize itself this way? Could the pattern be different elsewhere in the unobservable universe? Are voids truly empty? Or do they contain dark matter structures we simply can't detect? Standing inside a void galaxy and looking at the night sky would be a strange experience. Far fewer galaxies would be visible. the universe would appear emptier, lonelier. Astronomers in such a location might develop very different ideas about cosmic structure. We are lucky or perhaps randomly placed to live in a relatively dense region, where the universe appears full of galaxies. But the voids remind us that most of space is exactly that space. Emptiness dominates. Galaxy GNZ11 doesn't look like much in images, a faint reddish smudge barely visible against the black background of space. But this tiny blob represents something extraordinary, the most distant confirmed galaxy in the observable universe. Its light travelled an astonishing 13.4 billion years to reach us. When that light left GNZ11, the universe was only 400 million years old, a mere 3% of its current age. We are seeing this galaxy as it existed in the cosmic dawn shortly after the very first stars ignited. The galaxy appears so distant that its light has been profoundly stretched by universal expansion. Originally emitted in ultraviolet wavelengths, it now reaches us in the infrared. Its redshift value is 10.6, meaning the universe expanded by a factor of 11.6 since that light began its journey. Finding galaxies this distant requires extraordinary effort. They are incredibly faint. Their light has dimmed over billions of years of travel, and cosmic expansion has redshifted them out of visible wavelengths entirely. Only infrared telescopes can detect them, and even then it requires long, painstaking exposures. The James Webb Space Telescope, launched in 2021, is designed specifically to hunt these ancient galaxies. Its infrared vision can detect objects far beyond what Hubble can see. Early results from Webb have already revealed galaxies that might be even more distant than GNZ11, though confirmation requires detailed spectroscopy. Some of these candidate galaxies appear surprisingly mature. They contain organized structures, disk shapes, even hints of spiral arms that shouldn't exist so early in cosmic history. Standard models predict the first galaxies should look chaotic and irregular. Many of Webb's discoveries are already challenging these long-held expectations. One gamma-ray burst detected in 2009 came from even farther away, designated GRB ASEAN 9423. This explosive event occurred 13.2 billion light-years from Earth. It lasted only 10 seconds, representing the death throes of a massive star when the universe was just 630 million years old. The burst happened, but we didn't see it until billions of years later. The light carried news of an event that occurred before our solar system existed, before the Milky Way had formed its current structure, before most stars in the universe had been born. Think about the profound strangeness of observing such distant objects. We're not seeing them as they are now, we're seeing their ancient past. GNZ11 as it currently exists is impossible to observe. The light showing its present state won't reach Earth for another 13 billion years. By then our star will be dead, Earth will be gone, and no one will be here to see it. This creates a bizarre situation where the farthest objects we observe existed briefly in our past but are completely inaccessible in our present. We can study their baby pictures but never meet them as adults. Time and distance have separated us irrevocably. The observable universe has an edge, not a physical boundary, but a horizon beyond which we cannot see. This horizon exists because light from more distant regions simply hasn't had enough time to reach us yet. Every year this horizon expands by 1 light-year, revealing slightly more of the universe's ancient past. But here's the twist: dark energy complicates this. Objects beyond a certain distance are receding from us faster than light can travel through space. Their light will never reach us no matter how long we wait. These regions are beyond our cosmic event horizon, permanently inaccessible. The farthest galaxies we can observe are rapidly approaching this limit, venture much more distant, and they cross into the zone of no return. Some galaxies that existed in the early universe have already passed beyond this horizon. We'll never see them. Their light is trapped in a region of space expanding away from us at superluminal speeds. This means the observable universe isn't just limited by the speed of light and the universe's age, it's also profoundly limited by expansion itself. There's a maximum distance we'll ever be able to see. Even with perfect telescopes and infinite patience, we are racing against cosmic expansion to observe the farthest galaxies before they disappear from view. Some already have. More will inevitably follow. Right now, galaxies are vanishing from the observable universe, not dying or exploding, just accelerating beyond our cosmic horizon and winking out of detectability forever. The process happens slowly from our perspective. A galaxy that's barely visible now will gradually fade over millions of years as cosmic expansion carries it away. Its light will redshift further and further into infrared, then microwave, then radio wavelengths. Eventually it becomes so dim and redshifted that no telescope, no matter how powerful, could ever detect it. Dark energy drives this process. As space expands, the expansion rate remains roughly constant per unit distance. This creates an exponential effect. Distant regions recede faster than nearby ones. Beyond a certain distance, currently about 15 billion light-years, regions of space recede faster than light can travel. Light from galaxies at that distance is fighting a losing battle. It travels towards us at light speed, but the space between us and them expands even faster. The light makes progress, but the finish line keeps moving away faster than it can approach. It's like running on a treadmill that continuously speeds up. Here's what confirmed measurements tell us: roughly 95% of the observable universe is already beyond our cosmic event horizon. We can still see these regions because we are observing light emitted billions of years ago when they were closer and within our reach. But we will never see what's happening there now. That information is permanently inaccessible. Trillions of years in the future, assuming humanity or its descendants still exist, the night sky will look vastly different. The Milky Way will have merged with Andromeda, forming a giant elliptical galaxy. But the rest of the universe will have disappeared. Only nearby galaxies in our local cluster will remain visible. They're gravitationally bound, so expansion doesn't pull them apart. But everything beyond a few million light-years will have receded into invisibility. The cosmic microwave background will have redshifted beyond detection. Evidence of the Big Bang itself will vanish. Future cosmologists will face an extraordinary challenge. With no distant galaxies to observe, no cosmic background radiation to study, they'll struggle to ascertain that the universe began in a Big Bang. Their observations will suggest they live in an island universe, one giant galaxy surrounded by eternal darkness. Everything we know about cosmology will be unverifiable in the far future. The evidence will have literally disappeared over the horizon. Future scientists might develop completely wrong theories about the universe because critical evidence has become inaccessible. This is already happening in reverse. There are galaxies beyond our current event horizon that we will never observe. They existed in the early universe, emitted light towards us, but that light will never arrive. The space between us and them expanded too fast. We are permanently cut off from information about these regions. How many galaxies are we missing? Calculations suggest the actual universe contains far more galaxies than we can observe. If the universe is truly infinite, then the number of galaxies beyond our horizon is also infinite. We are observing an infinitesimally small fraction of what exists. Even if the universe is finite but very large, we are missing most of it. Current estimates suggest the total universe is at least 250 times larger than the observable portion. That means for every galaxy we can see, there are at least 250 galaxies beyond our view. Some of these might harbour civilizations. Intelligent species might exist in regions of space we'll never observe. They could have radio telescopes pointed our direction right now, wondering if anyone's out there, but the signals they send will never reach us. Cosmic expansion has severed any possibility of contact. The expansion is accelerating. Dark energy is becoming more dominant over time. This means galaxies are disappearing from our view faster than new ones appear. The observable universe will eventually shrink, not in physical size, but in its content. More and more galaxies will cross the horizon and vanish. We live in a special time. The universe is old enough that we can study its history through distant observations, yet young enough that most of the cosmic structure remains visible. Future observers won't have this luxury. The cosmos is hiding itself from us one galaxy at a time. Nothing travels faster than light. This universal speed limit creates an expanding prison from which no information can escape. Light moves at exactly 282 miles per second in a vacuum. Not approximately, but precisely. This speed is built into the very fabric of reality. Einstein's special relativity proved that accelerating any object with mass to light speed would require infinite energy. Photons having zero mass reach this speed naturally. This cosmic speed limit means information about distant events takes time to reach us. Light from our nearest star beyond our own takes over 4 years to arrive. Light from the Andromeda galaxy, our nearest large galactic neighbour, travels for 2.5 million years before reaching Earth. We see Andromeda not as it is now, but as it was 2.5 million years ago. Extend this logic to cosmic distances and the problem becomes severe. The farthest objects we observe exist in our deep past. Their present state is completely unknown. They might have evolved dramatically, collided with other galaxies, or even been destroyed by some catastrophe. We won't learn about any of this for billions of years. But the speed limit creates an even worse problem when combined with cosmic expansion. Space itself can expand faster than light travels. This doesn't violate relativity because space isn't an object. It's the stage on which objects exist. The stage can grow at any rate. Currently, galaxies roughly 15 billion light-years away are receding from us at light speed. Beyond that distance, they recede faster than light. This distance is called the Hubble radius. It represents the boundary between regions we might someday observe and regions forever beyond our reach. Wait though, if galaxies beyond 15 billion light-years recede faster than light, how can we see objects 13.4 billion light-years away? Shouldn't their light never reach us? The trick is that these objects were closer when they emitted the light we now observe. Their light was emitted when the universe was smaller, and those regions were within our Hubble radius. The light has been travelling towards us ever since fighting against expansion, but gradually making progress. However, light emitted today from galaxies beyond our cosmic event horizon will never reach us. The expansion carries them away faster than their light can approach. They've crossed a point of no return. The cosmic event horizon sits at roughly 15 billion light-years currently. This horizon is moving outward at light speed. Every second it expands by 186,000 miles. Every year it grows by 1 light-year in radius. New regions of space become theoretically observable as time passes. But here's where dark energy ruins everything. As space expands more, dark energy comes into existence, driving faster expansion. The acceleration means the cosmic event horizon isn't just moving outward, it's moving outward at an ever-decreasing rate. Eventually it will stop growing entirely. When expansion becomes fast enough, the cosmic event horizon will reach a maximum radius and stay there. Any galaxy beyond that distance will remain permanently unobservable. The acceleration will carry them away so fast that no amount of waiting will allow their light to reach us. Calculations suggest this limiting horizon sits somewhere around 60 to 70 billion light-years from Earth. That's the absolute maximum distance we could ever observe. Even with perfect instruments and infinite patience, everything beyond that is permanently beyond our ken. The light speed limit also affects our ability to communicate across cosmic distances. Any signal we send to a distant galaxy travels at light speed. If that galaxy lies beyond our cosmic event horizon, our signal will never arrive. Space expands faster than the signal can travel. The recipient recedes into inaccessibility before the message reaches them. This creates a communication horizon, separate from our observation horizon. We can observe galaxies in the distant past, but we can't send messages to them in the present. Any attempt to communicate fails because the expansion carries them beyond reach. We're trapped in an expanding bubble defined by light speed and cosmic expansion. The walls of this prison are growing, but not fast enough. More universe exists beyond our bubble than within it, and we have no way to access it. The speed limit isn't just a minor inconvenience. It's a fundamental barrier preventing us from observing most of reality. When astronomers measure a galaxy's distance, they're actually measuring how much its light has been stretched during its journey to Earth. This stretching, called redshift, turns the universe into a time machine. Light behaves as a wave. Like ocean waves, light waves have a wavelength, the distance between peaks. Blue light has short wavelengths around 450 nanometers. Red light has longer wavelengths around 700 nanometers. Different wavelengths produce different colours. When space expands, it literally stretches light waves travelling through it. A photon emitted in ultraviolet wavelengths might arrive at Earth as visible light, or even infrared, depending on how much space expanded during the photon's immense journey. Astronomers see this as a shift toward the red end of the spectrum, hence redshift. The amount of stretching directly reveals distance. A galaxy with a modest redshift is relatively nearby. Its light hasn't travelled long enough for significant stretching. A galaxy with extreme redshift is incredibly distant. Its light has been stretched enormously by expansion during a multi-billion-year journey. Redshift is quantified with the letter Z. A redshift of Zesa-1 means wavelengths have doubled. A redshift of Zesa-2 means wavelengths have tripled. The farthest confirmed galaxies have redshifts around 10 to 11, meaning their wavelengths have been stretched by a factor of 11 to 12. Here's where it truly becomes a time machine. Measuring redshift also measures time. The farther away a galaxy, the longer its light has travelled, and the farther back in time we're observing. Redshift and cosmic age are intimately linked through the expansion history of the universe. A galaxy at redshift Xeon-1 appears as it existed roughly 6 billion years ago. Redshift Xeon-2 shows the universe at 3 billion years old. Redshift Xeon-6 reveals the cosmic dawn around 900 million years after the Big Bang. Each observation peers into a specific ancient era of cosmic history. Astronomers measure redshift using spectroscopy. Light from galaxies contains absorption and emission lines, specific wavelengths where elements absorb or emit light. These lines create a unique pattern, like a fingerprint. Every element produces characteristic lines at specific wavelengths. By comparing where these lines appear in a galaxy's spectrum to where they should appear in a lab, astronomers calculate how much the wavelengths have been stretched. If hydrogen's emission line normally appears at 434 nanometers, but shows up at 868 nanometers in a galaxy spectrum that's a redshift of 1, the wavelength doubled. This technique works remarkably well. Modern spectrographs can measure redshifts to high precision. The Sloan Digital Sky Survey measured redshifts for millions of galaxies, mapping the three-dimensional structure of the universe across billions of light years. But redshift measurements come with caveats. Objects can also show redshift from their motion through space, a phenomenon called Doppler shift. A galaxy moving away from us will appear redshifted even without cosmic expansion. Nearby galaxies show redshift contributions from both expansion and their peculiar velocities, their individual motions relative to the average expansion. For distant galaxies, cosmological redshift overwhelmingly dominates. Their recession velocities from expansion dwarf any local motion. But for nearby objects, separating the two effects requires careful analysis. Redshift also affects brightness measurements. As light is stretched to longer wavelengths, it loses energy. Photons arrive less energetic than when they were emitted. This makes distant galaxies appear dimmer than their distance alone would suggest. Astronomers must meticulously correct for this when calculating luminosities. The most extreme redshifts reveal the earliest galaxies. These objects appear faint and red. Their light stretches from ultraviolet to infrared during the journey. Finding them requires infrared telescopes like James Webb. Hubble, optimized for visible light, largely missed these ancient systems. Each new redshift record represents pushing further into cosmic history. The current confirmed record sits around redshift 13, showing galaxies existing just 300 million years after the Big Bang. Webb might detect galaxies at redshift 15 or even 20, revealing an epoch when the first stars were just beginning to illuminate the darkness. Redshift has transformed astronomy into archaeology. We don't just study where objects are, we study when they were. Every observation is a glimpse into history preserved in light that's been travelling for eons. The universe's expansion has inadvertently created a vast archive of its own past, written in stretched wavelengths and encoded in ancient light. We're reading this archive one redshift measurement at a time. There's a wall in time we cannot see past, not because our telescopes aren't good enough, but because the universe itself becomes opaque beyond a certain point in its history. This fundamental barrier is the cosmic microwave background radiation, CMB, released 380,000 years after the Big Bang. It represents the momentous event when the universe cooled enough for atoms to form. Before this, the cosmos existed as an opaque, searing plasma. In the beginning, the universe was so hot that matter existed as free electrons and protons flying independently. This dense plasma scattered light constantly. Photons couldn't travel far before bouncing off electrons. It was like trying to see through an infinitely dense fog. The entire universe was opaque. As expansion cooled, the cosmos temperatures dropped below 3000 Kelvin. At this critical temperature, electrons finally combine with protons to form neutral hydrogen atoms. This process is called recombination, though it's actually the first time atoms formed, making the name somewhat misleading. With electrons now bound in atoms, they could no longer scatter light freely. The universe suddenly became transparent. Photons previously trapped could now travel unimpeded across space. The first light of the cosmos was released. These primordial photons have been travelling through space ever since. Over 13.8 billion years, cosmic expansion has stretched their wavelengths from visible light into microwaves. They arrive at Earth from every direction, creating a faint microwave glow filling the entire sky. This is the cosmic microwave background famously detected in 1965 by Penzias and Wilson. Its temperature is now a frigid 2.7 Kelvin, just above absolute zero. It represents the oldest light we can observe, a pristine snapshot of the universe as it appeared 380,000 years after its birth. The CMB forms an absolute barrier to optical observation. We cannot see anything earlier using light because light simply couldn't travel freely before recombination. The universe before this point is hidden behind an opaque wall of plasma. However, the CMB itself contains information about even earlier times. Tiny temperature variations across the sky, mere 1 part in 100,000, represent density fluctuations in the primordial plasma. These fluctuations were exquisitely seeded by quantum variations in the first fraction of a second after the Big Bang. Satellites like WMAP and Planck have mapped these variations with extraordinary precision. The patterns reveal fundamental properties of the universe, its age, composition, geometry, and expansion rate. The CMB has become cosmology's most important data set, but it also defines our ultimate observational limit. Before recombination, the universe is opaque to electromagnetic radiation. We might detect earlier events through other means, gravitational waves perhaps, or neutrinos that interact very weakly with matter. But optical and radio telescopes hit an insurmountable wall. Think about what this means. There's a surface in time beyond which we cannot observe using light. This surface, called the surface of last scattering, represents the farthest we can see with electromagnetic radiation. It exists at a redshift of roughly 1/100. The universe was 100 times smaller when this light was released. The CMB photons come from every direction, creating a spherical shell around us. This shell exists not in space, but profoundly in time. It represents a moment in history rather than a location. Every point we observe on the CMB sky shows a different region of the early universe, all observed at the same cosmic age. Observing the CMB is like standing in a dense fog. We see the fog itself as a uniform glow, but we can't see through it to what lies beyond. The fog in this case is the opaque plasma of the early universe. Beyond it, earlier times remain hidden. Scientists have proposed ways to probe even earlier epochs. The cosmic neutrino background, if detected, would carry information from 1 second after the Big Bang. Primordial gravitational waves might preserve imprints from the first trillionth of a second. These hypothetical signals could pierce the CMB barrier. So far, though, the cosmic microwave background remains our ultimate observational limit using electromagnetic radiation. It's a wall in time, not space. We can calculate what happened before it using the exquisite tools of physics, but we cannot directly observe those moments. The universe has hidden its earliest history behind this luminous fog. We see the fog with incredible clarity, but the darkness beyond it resists observation. Our view backward in time stops at the surface of a last scattering 380,000 years after the beginning. What happened before that? Theories suggest inflation quark gluon plasma, the formation of fundamental particles. But these remain beyond our direct view, hidden behind the oldest light in the universe. Astronomers face an impossible choice every time they design a survey. Go deep and see the faint, distant universe in exquisite detail, or go wide and map large areas with less depth. They cannot do both simultaneously with current technology. Telescope time is extraordinarily limited. Imagine you have 100 hours to observe the universe. You can point your telescope at one tiny patch of sky for all 100 hours, revealing incredibly faint objects in that single region. Or you can split your time across 100 different patches, spending 1 hour on each covering far more area, but achieving significantly less depth. The trade-off is fundamental. Collecting light takes time. Faint objects inherently require long exposures. The longer you stare at a patch of sky, the more faint objects appear. But every hour spent staring at one location is an hour not spent observing somewhere else. Wide surveys map large fractions of the sky. The Sloan Digital Sky Survey covered 1/3 of the heavens. It catalogued hundreds of millions of galaxies, but its depth was limited. Most observations lasted only a few minutes per field. Faint distant galaxies remained invisible. Deep surveys do the opposite. The Hubble Ultra Deep Field stared at one tiny patch for 11 days of total exposure time. It revealed nearly 10,000 galaxies in an area covering less than 1/10 millionth of the sky. Incredible depth, negligible coverage. Both approaches hold immense scientific value. Wide surveys reveal large-scale structure. They show how galaxies cluster into filaments and voids across billions of light years. These patterns constrain cosmological models. Understanding the cosmic web requires mapping large volumes. Deep surveys conversely reveal cosmic history. By detecting faint, distant galaxies, they show how the universe evolved. Early galaxies look vastly different from modern ones. Star formation rates have changed dramatically. Galaxy collisions were far more common in the past. Only deep observations reveal these distant objects. The ideal survey would be both wide and deep, comprehensive coverage with exquisite sensitivity. But this requires impossible amounts of telescope time. To survey the entire sky to the depth of the ultra-deep field would take Hubble millions of years. New surveys attempt to find a middle ground. The Dark Energy Survey covered 5,000 square degrees, a substantial area, while reaching moderate depth. It detected galaxies several billion light-years away. Though not as distant as the deepest surveys, the Legacy Survey of Space and Time LSST planned for the Vera Rubin Observatory will repeatedly image half the sky over 10 years. Each field receives multiple observations, building depth gradually while maintaining wide coverage. It's a pragmatic compromise approach, but even Rubin won't match the depth of dedicated deep fields. Physics imposes inherent limits. Light gathering power depends on telescope size and exposure time. Larger telescopes collect more photons per second. Longer exposures accumulate more total photons. But there's only so much you can do. The James Webb Space Telescope represents extraordinary light gathering power with a 6.5 meter mirror optimized for infrared, but its field of view is tiny. Surveying large areas deeply would take centuries. Webb excels at deep observations of small regions, not wide mapping. Next-generation surveys must choose their priorities. The Nancy Grace Roman Space Telescope will balance depth and coverage better than previous missions. Its wide-field camera can image areas 100 times larger than Webb's, while maintaining decent sensitivity, but it still can't survey the entire sky deeply. This fundamental trade-off affects what we know about the universe. We have excellent maps of large-scale structures out to a few billion light-years. Beyond that distance, coverage becomes spotty. We have spectacular images of tiny deep fields reaching back 13 billion years, but these might not represent typical regions. What if the deep fields happen to point at unusually dense or unusually empty areas? Small sample sizes create inherent uncertainty. Perhaps the early universe was more uniform than deep fields suggest, or perhaps it was more chaotic. Limited coverage makes it hard to say. Wide surveys might miss rare objects. If something interesting occurs in only one galaxy per billion, you need to survey billions of galaxies to find one. Narrow deep fields won't find such objects. Wide shallow surveys might miss them if they're faint. The trade-off creates critical gaps in knowledge. We know the nearby universe fairly well, and have detailed glimpses of the distant universe, but comprehensive mapping at all distances remains impossible. Astronomers must make hard choices. Study a few fields deeply, or many fields shallowly. Both approaches reveal important science, but both leave profound questions unanswered. Until technology improves dramatically, the depth versus coverage trade-off will continue limiting our view of the cosmos. We see fragments and samples, not the complete picture. In 1924, Edwin Hubble provided undeniable proof that galaxies exist far beyond the Milky Way. The universe suddenly became immeasurably larger than anyone had imagined. Hubble, in his pioneering work, estimated perhaps millions of galaxies existed in the observable cosmos. He was off by a factor of 1 million or more. Early surveys painstakingly counted galaxies by photographing the sky and examining the photographic plates by hand. Astronomers literally counted faint dots diligently, trying to distinguish fuzzy galaxies from individual stars. The Lick Observatory counted over 1 million galaxies in a survey completed in 1967. This seemed like an enormous number. Modern automated surveys have revised this figure upward repeatedly with astonishing speed. The Hubble Deep Field in 1995 revealed that apparently empty patches of sky contained thousands of galaxies, prompting initial estimates to jump to 100 billion galaxies in the observable universe. But that was just the beginning. Deeper surveys with progressively better instruments kept finding more. The Hubble Ultra Deep Field in 2004 showed nearly 10,000 galaxies in a tiny patch. Galaxy counts continued their relentless rise. In 2016, a team analysed all available deep field data and concluded the observable universe contains at least 2 trillion galaxies. Not 200 billion, but 2 trillion, 20 times previous estimates. Where did all these extra galaxies come from? They were always there, just too faint to detect. As telescopes improved, fainter galaxies became visible. Each advance in technology revealed more previously invisible systems. Many of these faint galaxies are dwarf galaxies, small systems containing millions to billions of stars rather than hundreds of billions. Individually unimpressive perhaps, but collectively numerous. For every large galaxy like the Milky Way, dozens or hundreds of dwarf galaxies exist. The 2 trillion estimate might still be too low. It counts only galaxies bright enough to detect with current technology. Even the deepest Hubble observations have detection limits. Fainter galaxies surely exist below this threshold. The James Webb Space Telescope is already revealing more. Webb's infrared vision detects galaxies invisible to Hubble. Early Webb observations suggest there might be even more galaxies than 2 trillion. Some estimates now cautiously approach 10 trillion galaxies, but the count gets complicated at high redshift. Very distant galaxies appear faint and small. Drawing the line between a mature galaxy and a proto-galaxy becomes arbitrary. Are we counting mature systems only, or including every clump of stars? Different surveys use different criteria, producing different counts. Some surveys count only galaxies above a certain mass threshold. Others include everything that resembles a gravitationally bound stellar system. Comparing counts across surveys requires careful attention to definitions. Here's the stunning escalation in raw numbers: 1924 millions, 1960s over 1 million catalogued, 1990s 100 billion estimated, 2016 2 trillion, 2025 possibly 10 trillion. Each decade brought dramatic upward revisions. The trend seems unlikely to stop. Better telescopes will inevitably reveal fainter galaxies. The true count might exceed 10 trillion. Some of these galaxies are massive ellipticals containing trillions of stars. Others are tiny dwarfs with barely 1 million stars. The size range spans factors of 1 million. Trying to count them all is like trying to count both elephants and ants, and calling them equivalent. The number that ultimately matters for cosmology isn't just the raw count, but the total stellar mass. How much matter is locked up in stars across all galaxies? This figure has changed less dramatically. Most of the mass resides in large galaxies which were counted relatively early. The newly discovered faint dwarfs add significantly to the count without adding much to the total mass. Still, the escalation is striking. We've gone from millions to potentially 10 trillion galaxies in a single century. Each upward revision serves as a humbling reminder of how little we have truly observed. And remember, these counts apply only to the observable universe. Beyond our cosmic horizon, more galaxies exist. If the universe is truly infinite, the total number of galaxies is also infinite. We are counting an infinitesimal fraction of infinity. Even within the observable universe, many galaxies remain undetected. They're too faint, too distant, or hidden behind impenetrable dust and gas. Our current count of trillions represents a lower limit. The true number could be substantially higher. Every time astronomers think they've counted most galaxies, improved instruments reveal vast populations they previously missed. The pattern suggests we're still far from a complete census. The universe is more crowded than we thought, and it keeps getting more crowded the harder we look. Our address in the universe just got significantly longer. Astronomers discovered in 2014 that the Milky Way belongs to a supercluster 100 times larger than previously thought. For decades, scientists knew we lived in the Virgo supercluster, a collection of galaxy groups and clusters spanning roughly 100 million light-years. Our local group containing the Milky Way and Andromeda sits on the outskirts of this structure. But measuring galaxy motions revealed something unexpected. The Virgo supercluster wasn't a separate, distinct entity. It's actually part of a much, much larger structure, defined by pervasive galaxy flows, streams of galaxies all moving towards a central gravitational basin. This megastructure is called Laniakea Hawaiian for immeasurable heaven. It contains roughly 100,000 galaxies spread across 500 million light-years. Our previous address was just a neighbourhood within a much larger, sprawling cosmic city. Laniakea's discovery came from meticulously mapping galaxy velocities. Galaxies don't just participate in cosmic expansion, they also move through space based on local gravitational attraction. By carefully subtracting the expansion velocity and examining only these peculiar velocities, astronomers mapped intricate gravitational flow patterns. The patterns revealed basins of attraction, vast regions where galaxies flow inexorably towards common centres. Laniakea represents one such immense basin. All 100,000 galaxies within it are slowly falling towards a central region dominated by the Shapley supercluster. The boundary of Laniakea isn't defined by where galaxies physically stop, but by where their flows diverge. At the edge, galaxies begin flowing towards different attractors. It's like a watershed rain falling on one side, flows to one ocean rain on the other side, flows elsewhere. This means superclusters can overlap and interpenetrate. Defining their boundaries requires choosing criteria. Using gravitational flow produces different boundaries than simply mapping galaxy density. Laniakea is vast using the flow definition, but its mass remains concentrated in subclusters like Virgo and Shapley. The Great Attractor sits near Laniakea's centre, a massive gravitational anomaly discovered in the 1970s. Our Milky Way and millions of other galaxies are being pulled towards it at an astonishing 600 kilometers per second. The Great Attractor itself is being pulled towards the even more massive Shapley supercluster. These motions happen over cosmic timescales. We're falling towards the Great Attractor at 600 km/h, which sounds fast, but translates to only 20 light-years per 1,000 years. At this rate, we won't arrive for billions of years, long after our stellar system has ceased to exist. Laniakea contains several prominent galaxy clusters. The Virgo cluster, with over 1,000 galaxies, dominates our local region. The Hydra and Centaurus clusters add more mass. The Shapley supercluster, containing thousands of galaxies, provides the ultimate gravitational anchor. But even Laniakea isn't necessarily the largest structure we're part of. Recent observations suggest Laniakea itself flows towards the Shapley attractor, which might be part of an even larger structure called the Pisces-Cetus supercluster complex. This vast filament stretches over 1 billion light-years. How far up does the hierarchy go? At some point, structures become so large they're no longer gravitationally bound. They participate fully in cosmic expansion rather than collapsing together. Laniakea sits near this boundary. It's marginally bound, meaning expansion and gravity are nearly balanced. In the far future, dark energy will likely pull Laniakea apart. Regions currently part of one flow basin will separate as expansion accelerates. What we now see as a unified structure will fragment into isolated pieces. For now though, Laniakea represents our cosmic neighbourhood on the larger scales. It's the region of the universe we share a common fate with all 100,000 galaxies slowly falling together towards a shared centre of mass. Mapping Laniakea required measuring velocities for thousands of galaxies. The Cosmic Flows project compiled these measurements, revealing the large-scale flow patterns. Future observations will refine the boundaries and identify even larger structures. But the discovery fundamentally changed our cosmic address. We're not just in the Milky Way and the local group in the Virgo supercluster, we're in Laniakea, a vast supercluster of superclusters. A basin containing 100,000 galaxies all flowing together through space. It's humbling. Our entire galaxy is one tiny part of 100,000 siblings, all caught in a gravitational dance spanning 500 million light-years. And this entire structure might itself be part of something even larger. Our place in the universe keeps getting smaller the more we learn. Massive objects bend space itself. Einstein predicted this profound truth in 1915 with his theory of general relativity. But seeing it happen took decades. When light from a distant galaxy passes near a massive cluster of galaxies, the cluster's immense gravity warps the fabric of space like a colossal, imperfect lens, distorting and magnifying the background galaxy. This creates spectacular optical illusions. A single background galaxy can appear as multiple images scattered around the foreground cluster. The galaxy's light takes different paths through the warped space, arriving from different directions. Astronomers see the same object repeated 4, 5, or even a dozen times across the sky. Sometimes, if the cosmic geometry is just right, it creates perfect circles called Einstein rings. The background galaxy, the lensing cluster, and Earth align so precisely that the galaxy's distorted image forms a complete luminous ring around the cluster. These are rare but utterly stunning when they occur. Gravitational lensing does more than create pretty pictures. It subtly tricks our observations. The magnification makes distant galaxies appear brighter and larger than they actually are. Without meticulously correcting for this, astronomers would miscalculate distances and luminosities. The Hubble Space Telescope found some of the most distant galaxies by strategically looking through massive cluster lenses. The cluster's gravity magnified faint background galaxies by factors of 10 or even 100, making them detectable when they would normally be too dim to see. But lensing also hides information. The distortion scrambles the galaxy's true shape. Astronomers see a stretched arc-shaped image rather than the galaxy's actual structure. Untangling the true appearance from the lensed image requires complex modelling and sophisticated computational techniques. Weak lensing creates even subtler effects. Distant galaxies appear slightly elongated by foreground mass, but not enough to create obvious arcs or multiple images. The distortion is tiny, a few percent at most. Individual galaxies show barely detectable stretching. However, measuring weak lensing for thousands of galaxies reveals the invisible mass distribution across vast scales. Dark matter doesn't emit light, but still bends space. By meticulously mapping how background galaxies are distorted, astronomers map dark matter across cosmic scales. This technique helped reveal the cosmic web, vast filaments of dark matter connecting galaxy clusters. Weak lensing traces these filaments even where no visible matter exists. The observations match computer simulations remarkably well, powerfully confirming that dark matter drives large-scale structure formation. The bullet cluster provided the most direct and compelling evidence for dark matter through lensing. Two galaxy clusters collided and passed directly through each other. The hot gas visible in X-rays stayed behind, slowed by friction during the collision. But weak lensing revealed that most of the mass passed straight through unimpeded without slowing. The lensing map showed two distinct mass concentrations perfectly separated from the X-ray gas. This definitively proved dark matter exists as an actual collisionless substance, rather than just a modification to gravity. Normal matter collided and slowed. Dark matter passed through collision-free exactly as theory predicted. But lensing creates observational challenges. When surveying distant galaxies, some fractions are magnified by foreground lenses. This creates a selection bias. Lensed galaxies appear in surveys more often than unlensed ones because the magnification makes them brighter. Accounting for this requires careful statistical corrections. Survey teams must estimate what fraction of detected galaxies are magnified and by how much. Get this wrong, and you'll miscalculate galaxy abundances and luminosity functions. Strong lensing also plays tricks with time. Light taking different paths around a massive lens travels different distances. When a background galaxy's brightness changes, say from a supernova explosion, we see the change at different times in different lensed images. Astronomers have observed this time delay effect in lensed quasars. One image brightens, then weeks or months later, another image of the same quasar brightens. The delay reveals the difference in light travel time between the paths. Measuring these delays helps constrain the expansion rate of the universe. The delay depends on the lens's mass geometry and the Hubble constant. Observations of multiple lens systems can independently measure cosmic expansion, offering a crucial cross-check for our cosmological models. Gravity bends light, creating a cosmic funhouse mirror. Every massive object between us and distant galaxies potentially distorts our view. We're observing the universe through an array of gravitational lenses, each one warping space in its own unique way. Most of what we see is subtly distorted. We just don't always notice. Something massive is pulling the Milky Way through space at a staggering 600 kilometers per second. This gravitational monster, dubbed the Great Attractor, sits roughly 250 million light-years away in the direction of the constellations Hydra and Centaurus. We can't see it clearly. The Great Attractor lies partially behind the zone of avoidance obscured by our galaxy's impenetrable dust and stars. Astronomers discovered it in the 1970s by meticulously measuring the peculiar velocities of galaxies, their motions through space beyond cosmic expansion. The pattern was unmistakable. Thousands of galaxies within hundreds of millions of light-years were all streaming towards the same unseen region. Something enormous was pulling them. Calculations suggested the attractor contained the mass of tens of thousands of galaxies, concentrated in a relatively small volume. But direct observation proved exceedingly difficult. Optical telescopes simply couldn't penetrate the Milky Way's obscuring dust. Astronomers resorted to other wavelengths. X-ray observations revealed hot gas from massive galaxy clusters. Infrared telescopes detected galaxies hidden by dust. Radio observations mapped hydrogen gas. These multi-wavelength studies revealed the Great Attractor isn't a single object, but a complex of massive galaxy clusters. The Norma cluster sits near the center, a rich cluster containing hundreds of galaxies. Surrounding it are several other massive clusters, all gravitationally bound together. The total mass estimate approaches 1,000 trillion times our Sun's mass. This enormous concentration of matter creates a gravitational well that utterly dominates local space. Everything within a few hundred million light-years feels its inexorable pull. But the mystery deepened. Even the Great Attractor itself is being pulled by something more massive still. The Shapley supercluster sitting 500 million light-years away contains even more mass. It's pulling the Great Attractor, which in turn is pulling us. We're caught in a hierarchy of gravitational flows, a cosmic cascade. These motions happen on timescales of billions of years. The Milky Way won't collide with the Great Attractor anytime soon. By the time we'd theoretically arrive, cosmic expansion driven by dark energy will likely have pulled the structure apart. We're falling towards something we'll never reach. The Great Attractor's location creates significant observational challenges. About 20% of the sky lies behind the Milky Way's disk. From our perspective, critical information about nearby large-scale structures remains hidden in this zone of avoidance. The attractor sits squarely in the worst obscured region. Recent surveys using radio and infrared have mapped more of this hidden region. The H.I. Parkes Zone of Avoidance, HIPAS survey, and the Hydra Centaurus Pavo Indus Hypersal survey revealed thousands of previously unknown galaxies behind the Milky Way. Many belong to clusters associated with the Great Attractor. These observations confirm that the Great Attractor contains several massive clusters rather than one monolithic supercluster. The Norma cluster anchors one side, the Centaurus cluster sits on the other. Between them lie smaller clusters and galaxy groups all gravitationally bound together. But mass estimates remain highly uncertain. Observations through the zone of avoidance are inherently incomplete. Some clusters might remain undetected. The total mass could be higher than current estimates suggest. The Great Attractor also affects cosmological measurements. When measuring cosmic expansion using nearby galaxies, their peculiar velocities towards the attractor create systematic errors. Expansion appears different when looking towards the attractor versus away from it. Cosmologists must meticulously correct for these local flows when calculating the Hubble constant. Ignoring local gravitational influences produces biased results. The Great Attractor's presence reminds us that the universe isn't expanding uniformly on small scales. While it exerts a powerful pull, some galaxies within our local group will eventually escape the attractor's grasp. Dark energy will drive expansion faster than the Great Attractor can pull things together. The structure represents a temporary configuration massive now, but doomed to fragment as space expands. For now though, it dominates our cosmic neighbourhood. The Milky Way, Andromeda, and thousands of other galaxies are all being pulled towards this hidden mass concentration. We're passengers on a journey through space driven by gravity from an object we can barely observe. The Great Attractor sits there in the zone of avoidance, pulling half the local universe towards it, while remaining largely invisible, a gravitational giant hiding in plain sight behind our own galaxy's dust. Turn off visible light and turn on radio wavelengths and the universe transforms into something almost unrecognizable. Objects that shine brilliantly in optical wavelengths vanish. Things utterly invisible to normal telescopes suddenly dominate the sky. Radio waves are light waves with wavelengths measuring millimeters to meters, thousands to millions of times longer than visible light. Our eyes cannot detect them, but radio telescopes can. When astronomers first built crude radio telescopes in the 1930s, they discovered a completely different cosmos. Normal stars are nearly invisible in radio wavelengths. The optical night sky, filled with billions of glittering stars, becomes mostly empty in radio. What appears instead exotic objects that barely show up in visible light. Radio galaxies become the dominant beacons. These systems harbour supermassive black holes actively consuming matter. The infalling material doesn't fall straight in. It forms an accretion disk heating to millions of degrees. Powerful magnetic fields channel some of this material into jets shooting outward at nearly the speed of light. These jets extend for hundreds of thousands or even millions of light years. When the jet material slams into intergalactic gas, it creates enormous lobes that glow brilliantly in radio wavelengths. A single radio galaxy can span distances larger than dozens of Milky Ways placed end to end. In visible light, you might see a small, unremarkable galaxy. In the radio, that same galaxy appears as a monster, with vast wings of emission stretching across the sky. The radio structure dwarfs the optical galaxy by factors of 100 or more. Pulsars rapidly spinning neutron stars emit powerful focused radio beams. They're virtually invisible in optical wavelengths, but shine like cosmic lighthouses in radio. Their regular pulses ticking dozens to hundreds of times per second can be detected across thousands of light years. The cosmic microwave background invisible to our eyes completely dominates the microwave portion of the radio spectrum. This ancient light fills the entire sky with faint radiation left over from the Big Bang. Radio telescopes designed specifically to observe it see a universe bathed in primordial glow. Cold hydrogen gas, the ubiquitous raw material for star formation, emits radio waves at a specific frequency, 420 MHz, the 21 Cinterotia line. This emission allows astronomers to map hydrogen throughout the universe. Vast reservoirs of gas invisible in optical wavelengths appear clearly in radio observations. Supernova remnants glow in the radio. The expanding shells of gas from stellar explosions emit radio waves as they plough through the interstellar medium. Some remnants are spectacularly bright in radio but barely visible optically. Even our own galaxy looks profoundly different. The Milky Way's spiral structure becomes more apparent in radio observations of hydrogen gas. Star-forming regions glow in radio from ionized gas. The galactic center, heavily obscured by dust in visible light, reveals itself in radio and shows structures invisible to optical telescopes. Radio observations pierce through the thick dust that blocks visible light. The zone of avoidance, that 20% of the sky obscured by our galaxy, becomes partially transparent in radio. Astronomers can detect galaxies and clusters hidden behind the Milky Way's dust lanes. But radio astronomy has its own limitations. Radio wavelengths are much longer than visible light, which means radio telescopes need enormous size to achieve good resolution. A single radio dish produces fuzzy, low-resolution images. To see fine details, astronomers combine multiple telescopes into arrays. The Very Large Array VLA in New Mexico links 27 dishes across 22 miles. Together they achieve resolution rivaling optical telescopes. Even larger arrays like ALMA in Chile and the Event Horizon Telescope spanning the entire Earth push resolution further. Different wavelengths reveal different physics. Optical light traces stars and hot gas. Radio waves reveal cold gas magnetic fields and relativistic particles. Combining observations across wavelengths provides a more complete, nuanced picture. Some objects are radio loud. They emit more energy in radio than visible light. Quasars often fall in this category. Others are radio quiet, appearing bright optically but faint in radio. The radio universe isn't just a different view of the same cosmos. It reveals phenomena and structures that optical astronomy alone would never detect. Turn on radio eyes and new universes appear, jets pulsars, cold gas clouds, and the ancient microwave echo of creation itself. We're not just observing the universe in multiple wavelengths. We're observing multiple universes, each one revealing phenomena invisible to the others. The X-ray sky is violent. Objects that appear calm and serene in visible light reveal their explosive high-energy nature when observed in X-rays. These high-energy photons come from matter heated to millions of degrees, temperatures that would instantly vaporize any known material. Our atmosphere blocks X-rays completely, which is fortunate because cosmic X-rays would be deadly to life. But it also means X-ray astronomy requires expensive space-based telescopes. The first X-ray observatory Uhuru launched in 1970. It immediately revealed a universe far more energetic and violent than visible light observations had ever suggested. Black holes dominate the X-ray sky. When matter falls towards a black hole, gravitational energy converts to intense heat. The material spirals inward through an accretion disk heating to temperatures exceeding 100 million degrees. At these extreme temperatures, atoms emit X-rays. A supermassive black hole actively feeding can outshine its entire host galaxy in X-rays while appearing relatively faint in visible light. The X-ray emission comes from a tiny region near the black hole, sometimes smaller than our solar system. Yet it radiates more energy than billions of stars. Neutron stars also shine brilliantly in X-rays. These stellar corpses pack more mass than our Sun into a sphere just 12 miles across. Their surfaces reach millions of degrees. Some neutron stars in binary systems pull material from companion stars, creating X-ray sources so bright they were among the first cosmic X-ray sources discovered. Galaxy clusters revealed their true nature through X-rays. What appears in visible light as a scattered collection of galaxies becomes in X-rays a vast cloud of superheated gas. This intergalactic medium, heated to tens of millions of degrees, contains more mass than all the galaxies combined. The gas fills the space between galaxies, glowing fiercely in X-rays but utterly invisible to optical telescopes. The Chandra X-ray Observatory revealed extraordinary details. X-ray images of galaxy clusters show gigantic bubbles blown by supermassive black holes. The black holes at cluster centers inject enormous energy into the surrounding gas, creating cavities hundreds of thousands of light years across. Supernova remnants create spectacular X-ray sources. The expanding debris from stellar explosions slams into surrounding gas at thousands of miles per second, creating shock waves that heat material to millions of degrees. Young remnants like Cassiopeia A shine brilliantly in X-rays, revealing the violent physics of stellar death. The hot gas around galaxies came as a profound surprise. Our own Milky Way is surrounded by a halo of gas at 1 million degrees. This corona remains invisible in visible light but glows faintly in X-rays. Where this hot gas came from and how it stays hot remain active research questions. X-ray binary systems, where a normal star orbits a black hole or neutron star, create some of the brightest X-ray sources in galaxies. Material pulled from the normal star spirals towards the compact object, heating to X-ray emitting temperatures. These systems flicker and flare, sometimes brightening by factors of thousands in mere hours. Active galactic nuclei AGN appear modest in visible light but dominate in X-rays. The supermassive black holes at galactic centers emit prodigious X-ray radiation when actively accreting matter. Surveys at X-ray wavelengths reveal millions of these active nuclei, many of which show minimal optical emission. The cosmic X-ray background, a diffuse glow of X-rays coming from all directions, puzzled astronomers for decades. Chandra and XMM Newton eventually resolved this background into individual sources. Most are distant active galaxies. Collectively, millions of supermassive black holes across cosmic history created this omnipresent X-ray fog. The deepest X-ray surveys, staring at small patches of sky for weeks, detect supermassive black holes across most of cosmic time. These observations powerfully show that black hole growth and galaxy formation are intimately connected. Nearly every massive galaxy harbours a supermassive black hole that was active in the past. X-ray observations reveal hidden populations. Some active galactic nuclei are so heavily obscured by dust that visible and even infrared light can't escape, but X-rays penetrate the dust, revealing black holes invisible at other wavelengths. Transient X-ray sources appear and disappear. Stellar flares, tidal disruption events where stars are torn apart by black holes, and neutron star mergers all create temporary X-ray beacons. Monitoring the X-ray sky reveals a dynamic universe of violent high-energy events. The X-ray universe is hotter, more energetic, and profoundly more violent than the visible cosmos. It reveals the extreme physics happening around the most compact objects, black holes, neutron stars, and shock-heated gas. Without X-ray observations, we'd miss half the story of how matter behaves under the most extreme conditions the universe can create. Turn on X-ray vision, and the calm optical sky transforms into a scene of cosmic violence. The oldest galaxies in the universe are fundamentally invisible to human eyes. Their light emitted as ultraviolet and visible wavelengths billions of years ago has been profoundly stretched by cosmic expansion into infrared. To see the earliest galaxies requires infrared vision. This is precisely why the James Webb Space Telescope was built with infrared detectors rather than optical ones. Webb's mirror, covered in a thin layer of gold to enhance infrared reflection, collects light that left distant galaxies when the universe was just a few 100 million years old. The Hubble Space Telescope, optimized for visible and ultraviolet light, could glimpse these ancient systems, but not study them in detail. The galaxies appeared as faint red dots at the absolute limit of detection. Webb sees them clearly, revealing structures and properties invisible to earlier telescopes. Infrared penetrates dust that blocks visible light. Star-forming regions are often shrouded in thick dust clouds. Visible light gets absorbed and scattered. Infrared passes straight through, allowing observations of stars forming deep inside molecular clouds. This capability alone revolutionizes our understanding of star formation. But infrared's biggest advantage is accessing high redshift galaxies. A galaxy at redshift 10 emits most of its light in ultraviolet wavelengths. By the time this light reaches Earth, expansion has stretched it into infrared. The farther away a galaxy, the more its light redshifts. The most distant galaxies only appear in the infrared. The first Webb observations revealed galaxies that might exist at redshift 15 or higher. These systems existed just 200 million years after the Big Bang. Their light has been travelling for over 13.6 billion years, arriving at Earth as faint infrared photons. Some of these early galaxies look surprisingly mature. They show organised structures, disk shapes, even hints of spiral arms. Standard models predicted the first galaxies should appear chaotic, with irregular shapes and active mergers. Many of Webb's discoveries are already challenging these predictions. Dusty galaxies also reveal themselves prominently in infrared. Some galaxies form stars so prodigiously that dust production outpaces supernova clearance. These systems become shrouded in their own dust-blocking visible light. They're nearly invisible to optical telescopes but shine brilliantly in infrared. Sub-millimeter observations, even longer infrared wavelengths, detect the coldest dust. This traces star formation in the most obscured galaxies. Surveys at these wavelengths revealed vast populations of dusty starburst galaxies that optical surveys completely missed. The infrared sky looks vastly different from the optical sky. Cool stars, red dwarfs and brown dwarfs become prominent. These objects emit most of their light in infrared. Optical surveys barely detect them, but infrared observations reveal billions across the galaxy. Planets around other stars glow in the infrared. While stars overwhelmingly outshine planets in visible light, the contrast is much better in infrared. This makes infrared optimal for imaging exoplanets directly. Several planetary systems have been photographed using infrared adaptive optics. The centre of our galaxy, heavily obscured by dust in visible wavelengths, appears clearly in infrared. Astronomers can track stars orbiting the supermassive black hole at the galactic centre. These observations, impossible in visible light, proved a black hole exists there and measured its mass to high precision. Infrared observations reveal protoplanetary disks around young stars. These dusty disks, warmed by the central star, emit infrared radiation. Studying them shows how planetary systems form. Gaps in the disks often mark where planets are currently forming. The Spitzer Space Telescope, operating from 2003 to 2020, surveyed large areas in infrared. It detected millions of galaxies invisible to optical telescopes. Its deep surveys revealed star formation hidden by dust across cosmic history. The Wide-Field Infrared Survey Explorer WISE mapped the entire sky in infrared. It catalogued hundreds of millions of objects, dusty galaxies, cool stars, asteroids, comets. The survey revealed populations of objects that optical sky surveys missed entirely. Water. A key molecule for life has absorption features in infrared. Observing these features reveals water in interstellar clouds around young stars and potentially in exoplanet atmospheres. Characterizing exoplanet atmospheres relies heavily on infrared spectroscopy. But infrared astronomy faces unique challenges. Earth's atmosphere glows brightly in the infrared from its own heat. Ground-based infrared telescopes must contend with this bright foreground. Space-based observatories avoid this problem but require cooling to extremely low temperatures. Webb operates at -370 degrees Fahrenheit to minimize its own infrared glow. A massive sun shield blocks heat from the solar system, allowing the telescope to stay cold enough that its own heat doesn't overwhelm faint cosmic signals. The universe's oldest light hides in the infrared. The earliest galaxies, the most obscured star formation, cool brown dwarfs and exoplanet atmospheres all reveal themselves at these wavelengths. Without infrared vision, we'd miss the cosmic dawn entirely. The ancient universe only appears when we see in wavelengths our eyes cannot detect. The observable universe contains roughly 2 trillion galaxies spanning 93 billion light-years. But this might be just the tiniest fraction of what truly exists. If the universe is infinite, then everything we can observe represents exactly 0% of the total. Cosmologists honestly don't know whether the universe is finite or infinite. Measurement suggests space is very flat, which is consistent with infinite extent. But flatness alone doesn't definitively prove infinity. A very large, finite universe could also appear flat just as Earth's surface appears flat locally, despite being curved globally. If space extends infinitely in all directions, then it contains infinite matter, infinite galaxies, infinite stars, and infinite planets. Our observable bubble sits within this infinity like a single grain of sand within an infinite desert. Nothing we observe from within reveals where this infinite desert surrounds us. An infinite universe creates profound conceptual problems. Within infinity, every possible arrangement of matter that doesn't violate fundamental physics will occur somewhere, not just once, but infinitely many times. Somewhere in an infinite cosmos there might be an exact copy of Earth, complete with duplicates of every person who has ever lived. This sounds like science fiction, but it's a logical consequence of infinity combined with finite building blocks. If you shuffle a finite deck of cards infinitely many times, every possible arrangement will appear infinitely often. The same principle applies to matter arranged in space. The probability of finding an exact duplicate Earth in any given random volume is essentially zero. But multiply zero probability by infinite volume and the mathematics says duplicates must exist. An infinite universe doesn't just allow for copies, it requires them. Some cosmologists find this deeply disturbing. Others argue it changes nothing practical. These duplicates, if they exist, lie beyond our cosmic horizon and always will. We can never observe them, visit them, or communicate with them. They might as well exist in separate universes entirely. An infinite universe also means the question, how much have we observed, has a trivial answer 0%. You can't observe a finite fraction of infinity. Every number divided by infinity equals 0. No matter how much our observable universe expands, we'll never observe more than 0% of an infinite cosmos. This makes certain cosmological questions meaningless. What's the average density of the universe? Has no answer if the universe is infinite and non-uniform. You can calculate average density within the observable region, but extrapolating to infinity creates insurmountable problems. Inflation theory, which describes the universe's early rapid expansion, generically predicts an infinite universe. If inflation occurred, space likely expanded to infinite size during the inflationary epoch. The theory doesn't strictly require infinity, but most versions produce it naturally. Observational tests can potentially distinguish between a finite and infinite universe. Measuring space's curvature with high precision could reveal positive curvature, which would definitively prove the universe is finite. So far, measurements show flatness within error bars, leaving both possibilities open. A positively curved universe would loop back on itself like a sphere's surface. Light travelling far enough in one direction would eventually return from the opposite direction. We could theoretically see multiple images of the same galaxy in different parts of the sky. Searches for such repeating patterns have found nothing. The cosmic microwave background provides the most precise curvature measurements. The pattern of temperature fluctuations depends on space's geometry. Current data are consistent with flatness. suggesting either infinite extent or a finite universe, much, much larger than the observable region. If the universe is finite but very large, say 1,000 times the observable universe, we'd have no way to tell from inside our cosmic bubble. The curvature would be too slight to detect. We'd observe apparent flatness even though space actually curves. Philosophers debate whether infinity truly exists in nature or is just a mathematical abstraction. Physics equations contain infinities, but perhaps these represent limits of the theory rather than physical reality. Perhaps something prevents true infinity from manifesting in the actual universe. For practical astronomy, the question matters little. We can only observe the observable universe regardless of what lies beyond. Our theories must work within this bubble, whether an infinite or finite universe surrounds it. But intellectually, the question profoundly affects how we think about existence. Are we one planet in one galaxy, in one observable bubble within infinity, or are we a measurable, however tiny fraction of a large but finite cosmos? The answer determines whether how much we've observed is 0% or some tiny but non-zero fraction. Until observations definitively reveal space's true geometry, both possibilities remain open. We might live in an island universe or within an infinite expanse. The cosmos isn't telling us which. Technology improves constantly. Telescopes get bigger, detectors become more sensitive, and image processing algorithms grow more sophisticated. But fundamental physics imposes limits that no amount of engineering can overcome. Light gathering power depends on mirror size. Larger mirrors collect more photons per second from faint objects. The James Webb Space Telescope's 6.5-meter mirror collects more light than Hubble's 2.4-meter mirror. Future telescopes might reach 30 meters or even larger. But building such monsters presents enormous, unprecedented challenges. The mirror must maintain its shape to nanometer precision. Temperature variations, vibrations, and gravity all subtly distort the surface. Keeping a 30-meter mirror stable enough for high-resolution imaging requires extraordinary engineering and material science breakthroughs. Ground-based telescopes face atmospheric turbulence. Air currents blur starlight-limiting resolution. Adaptive optics partially correct this by using deformable mirrors that adjust thousands of times per second. But perfection is impossible. Space telescopes avoid the atmosphere entirely, achieving resolution, limited only by mirror size and light's fundamental wavelength. Diffraction, the bending of light waves around obstacles, creates ultimate resolution limits. Light waves bend around edges, creating diffraction patterns. Smaller wavelengths diffract less, allowing better resolution. This is why ultraviolet telescopes, all else being equal, achieve better resolution than infrared telescopes of the same size. These aren't just engineering hurdles, they are fundamental physical boundaries. We stand at the precipice of understanding, armed with instruments that extend our senses across billions of light years and billions of years. Yet the deeper we look, the more profound the mysteries become. The universe is a vast, beautiful, terrifying enigma, most of which remains forever hidden beyond the reach of our sight, our instruments, and perhaps even our comprehension. We are but transient observers in a cosmic drama whose beginning we can barely glimpse, and whose end will happen long after our brief flicker. We collect fragments, piece together samples, and try to construct a coherent narrative from whispers and shadows. But the ultimate truth of the cosmos, its true scale, its unseen forces, its infinite possibilities, and its very nature remains a secret it may never fully reveal. The universe continues to expand, to accelerate, to evolve forever, holding more questions than answers, a testament to the enduring human spirit of inquiry, forever gazing into the overwhelming unknown.